Question 2, Part A. Explain why transition elements have variable oxidation states. So this is always a standard answer. The 3D and 4S subshells, they are similar in energy. So there is a reason there. I give you two elements to compare: calcium and iron. So let's say now calcium. Calcium, we know that is always form 2 positive, because the 4s electrons, once is removed, it's quite hard to remove the third electron from the 3p. So the 3p is of course octet configuration, and is closer to the nucleus. So the electrons in the 3p is relatively harder to remove. That's why calcium, normally it will not really form calcium 3, calcium 4 ion, because the energies level between the 4s and 3p, they are quite far. In fact, they are in different shells, right? But this one is different, means the energies levels is difference between the 3D and 4S. We know that 3D and 4S, the energies level, they are quite close. Actually 3D is somewhere here. I bring it nearer so you can see that clearly. So it's actually somewhere here. So for this iron, we know that iron can form iron 2 and iron 3. So let's say the 2 electrons removed from 4s, because the energies levels between the 3D and 4s subshell, they are close. That's why when these 2 electrons remove, it's relatively easier to remove electrons from 3D. Right? So it means if, let's say, the 2 electrons removed from 4s, it will form Fe2. If, let's say, now this iron 2 need to remove another electrons to form iron 3, is easy, because it need to remove 1 electron from 3D, which is further away from the nucleus. So we say that because 3D and 4s, these subshell, they are similar in energy, that's why it can form different oxidation states or different oxidation number. Right, that's the reason. Part B. Sketch the shape of 3DXY. So this one you have to be careful. Whenever they say XY, XZ, YZ, means you have to draw 4 loops, and these 4 loops must between the axis. In this case is the XY axis. Now the XY axis is here, X and Y. So you have to draw 4 loops between the axis like this, 1, 2, 3, 4. So when you draw the 4 loops between the X and Y axis, then you get the 1 mark. Right? So as long you can draw it nicely. Okay, that's how you deal with this drawing. Part C. Explain why transition elements from the color compound. So transition elements always can form different color or the color compound. So the color compound, first thing that you must mention is the DD splitting. So when the transition elements before is form the dative bonds with the ligand, is something like this one. So all the d orbitals, they are degenerate, means same energies level. Okay, after the ligand approach and form dative bonds, so these d orbitals will feel the extra repulsion, and it will go to higher energy level, means it will split. So it will split to two sets, and something like this. This is the octahedral complex formation, means the d orbitals now is split to two sets. So the actually for these orbitals, they have their names. This one is dz square, dx square y square, dxy, dyz, dxz. So these are the d orbitals, right? So two sets. So these two sets we call non-degenerate orbitals. Means these two sets of orbitals, they are now having different energies level, right? So this one we call DD splitting. DD splitting. So first point, you must say that because the ligand approach form native bond with transitions metals, so therefore it's undergo DD splitting. After that, you need to mention the absorptions of light. Let's say there is one electrons in the lower d orbitals, and this electron will absorb the frequency or wavelength in visible spectrum. So these electrons will get excited or is get promoted. So this is the second point you must mention. The electrons in lower energies orbitals will absorb visible light and get excited. Because the light is being absorbed, we cannot see the particular light. We will see the complementary light. Means the complementary of the light that being absorbed. So again, the light that being absorbed will not be seen. We will see the complementary color. Part D, aqueous solution of copper 2 salts. It has this hexa aqua copper 2 ions. Now we have this equilibrium 3 and 4. The 3 is the hydroxide with this complex ion, form this copper hydroxide with the 6H2O. Equilibrium 4 is the this hexa aqua copper 2 with the ammonia, form this complex ion. If you want to know the name, so this is the name, tetraamine diaqua copper 2. So tetraamine means 4 ammonia, okay, diaqua means 2 H2O, so copper 2 ion. Now part 1, state the color of the copper 2 hydroxide and this tetraamine diaqua copper 2 ion. So no choice, this one you must memorize. Any things or any colors about copper and cobalt complex ion, you must know. So for the copper hydroxide is pale blue precipitate. You might not really need to say precipitate because it's just as color. So you just say pale blue. For this tetraamine diaqua copper 2, so it's dark blue or deep blue. Part 2. Use the Le Chatelier principle to explain why a precipitate is formed when sodium hydroxide is added dropwise to this hexa aqua copper 2. So when this hydroxide is added dropwise, so means concentration of the hydroxide increases. So addition of hydroxide will increase the concentration of hydroxide. So therefore, equilibrium will shift to right. This is very easy, something that you learn in AST. Part E. This is the drawing about the complex ion. So it's always asked, and it's very common in the exam papers. Draw the two possible stereoisomers with the formula. Okay, this one, the tetraamine diaqua copper 2. So from here you can see that they are all monodentate ligand. 4 ammonia, 2 H2O. So therefore, it will form two stereoisomer, which is cis and trans. So this is confirmed. Again, this one will not form opticals because no bidentate ligand. So when it's all monodentate ligand, it just can form cis and trans. Normally, we will focus on the monodentate with these two dative bonds. Means the monodentate that form two dative bonds with the copper. In this case, is the water. So the H2O. Because it's easy to compare. We look at the positions, or we put the positions of this H2O. When this H2O is opposite like this, the bond angle between this OCOO is 180 degree. So this one is the trans isomers. If now we put H2O now at the same side, the bond angle is 90. So means the OCOO is 90. So this one is the cis isomer. We say that these two monodentate ligand, the same one, they are at the same side. So this is a cis isomer. So you need to draw these two stereoisomers. Okay, I hope you understand, and thank you.